session. Our first speaker will be Zong-Liang from UT Austin. He's a professor at UT Austin Jackson School. He was a co-chair for NCAR working group, land model working group before. And right now he's the founding director for the Center for Integrated Assistance Science at UT Austin. So he will talk today about the generalized land surface process from theory, observation, modeling, and applications. Let's welcome Zong-Liang.
Some materials went too fast. I go through too fast. Don't worry about them. You can always download them from the my website. Go to the courses. You will see the list of courses where I teach, and you can download the materials from there. I see from the audience we have lots of students. Maybe many of you are very familiar with clouds, microphysics, aerosols. May not be really familiar with land surface processes. That's why I want to give some brief introduction to land surface processes. We know that land is really important. There's no need to emphasize this importance. We all live on land. Land provides us with shelter, food, the infrastructure and clothing. And all extreme events we are familiar with, such as droughts, flooding, the dust, fires occur on land. And land compared to oceans, maybe I'm land-centric, compared to oceans, land surface is highly heterogeneous, very complex, and you will see lots of multi-scale interactions and really requiring multidisciplinary collaborations. We also know that land surface landscape can be rapidly modified by humans, and how the interaction between the modified systems and the natural systems, between humans and the natural systems, has been really a topic for intense study. We have seen this figure earlier today showing the climate forcings. Past focus has been on aerosols, greenhouse gases. However, on global scales, those may be very, very important. But at regional scale, urbanization, land use, land cover change could introduce the changes in regional climate of a similar or maybe greater magnitude. And so therefore, how to study land and the role in climate change at a regional scale has been a very important topic. Now let me give a quick overview or history of land surface processes and modeling in Earth system models. This figure was modified from IPCC earlier 1970s or late 1960s. The land just like a bucket in global climate models. Later on, in 1980s, beds, SIB were introduced to represent role of vegetation in regulating land-atmosphere interaction. I think everyone understands the acronyms here. BEDS stands for Biosphere Atmosphere Transfer Scheme. SIB stands for Simple Biosphere Model. Even it's very simple, but actually it's not that simple. Because the many models that have been developed after BEDS and SIB to pioneer land models, so we really want to know the relative strength and weaknesses of all of those models, more than 20 models or 30 models. Almost every day if you look at literature, there's a new model being developed. So the PILBS was formed, which is one of the first MIPS model intercomparison projects. That was formed to intercompare the different models, trying to understand the relative strengths and weaknesses of these models. That was a part of my PhD, working under Henderson Sellers in Australia. So I really had an experience to go from northern hemisphere to southern hemisphere, and then from eastern hemisphere to western hemisphere to see all different kind of landscapes. Based on PILBS, and we realized we really need to integrate strengths from different models. That's how we got the CLM. Early on, it was called common land model. Later, because this model has been adopted by NCAR, all the components in NCAR model called community, has a community in the beginning. So common land model became community land model. So those, whenever we talk about science, in any science, any fields, we need to honor pioneers. For distinguished scientists here, you all know who they are. But for young scientists, especially for students, Manabi, we heard about that a lot. He's a pioneer in many fields: radiation, oceans, atmosphere, GCM. He was the first to put a bucket land hydrology model into GCM. Bob Dickinson, I did a postdoc with him. He's my colleague. We are on the same floor at UT Austin. Pierre Sellers, SIB, after he published SIB and many siblings, many papers, and he became astronaut working in Houston. And I think now he's retired from being astronaut. He's in administrator in NASA. Henderson Sellers, she started PILBS. So now let's look at the CLM. I was fortunate to be the co-chair of this land working group with Dave Lawrence from NCAR. I served as a co-chair for 2 terms. During that period, the CLM has evolved greatly from, as you can see, from the 3.5, first of all, from 3 to 3.5, and then to 4, and then 4.5. You can see names, lots of names there. And also, recently, you can see this name structure very similar to what you would see from IPCC. You have coordinating lead authors, and contributing authors. So land model really represents a team effort from a broad community. This is CLM, and this cartoon-like of representation of the model. You can see the model indeed has 3 basic major processes: energy, biogeophysics, or surface energy balances, and also which has soil temperature, soil moisture calculation, and surface energy balance, which also deals with boundary layer processes, and also radiative transfer, like solar radiation, long-wave radiation through the canopy. And then we have hydrological processes, which deal with the precipitation, interception, and drip, throughful, and snow melt, and freezing, thawing processes, as well as others like rivers and the wetlands-related hydrological processes. And then biochemical cycles. This is when you have everything linked as a landscape. You see there's a constant human modification of landscape, urbanization, irrigation, and afforestation, deforestation, things like that. These are ongoing. Next, Dr. Zong-Liang will give how human activities would modify landscape and how that can be represented. Hopefully, she will. We're looking forward to the wonderful talk from her after my talk. 4.5 compared to 4, not major changes, but some details have been introduced, mainly related to the transpiration and ponded water introduced in hydrology, because earlier, whenever you have a free standing water, they immediately goes runoff on land surface. But now that is introduced to exist over the land before they disappear. And also there are lots of changes in the biogeochemical part of the model, as well as the river routing and the crops irrigation aspect of the land model. This is a summary of evolution during the term when I was the co-chair with developments from 3 to 3.5, mainly including my group's hydrological work, and to 4 and 4.5. And next year, 5 will be released. So really, the model is being developed very quickly. For university communities, this has been challenging to keep up to the rapid development of effort at NCAR, because we have dedicated scientists in universities. We train students. When they become familiar with the model, they graduate, they move on. So we have to train the new students again. That's a challenge we are facing. Just like in the US, basketball coach in the college versus a professional coach in NBA, NFL. So different cultures. So now let me summarize the generalized land surface processes, really not just the traditional way of thinking of including momentum change, energy exchange, water, and trace gases between land and atmosphere. We should really consider this land memory processes. Like memory can be stored in vegetation phenology, snowpack, ice, soil moisture, groundwater, as well as the terrain. So this play a very important role in intra-seasonal to seasonal interannual climate variability. And also we need to emphasize that human activities, this make things very interesting. Unlike oceans, the land dramatically can be modified by humans. So next, I'm going to use one example showing another modeling effort by my group. Based on experience we have learned from developing CLM and seeing its evolution in different use. So we figured another wider use model in WRF, in limited area weather prediction model, NOAA, which needs a significant upgrade. So my group takes the challenge to upgrade NOAA MP. From that, we think that represents a paradigm shift in land surface modeling. I'm going to explain what NOAA MP stands for. Anyway, this effort has been supported by scientists from different institutions with funding from NOAA. The current status in land surface modeling development looks like this. Everybody knows the land surface model. It represents exchange processes in terms of characteristics, states, and fluxes between land and atmosphere. And there's a rich body of literature in modeling each of these biogeophysical and biogeochemical processes. However, when you, based on each individual schemes for example, runoff, temperature, soil moisture, you can develop a model such as BETS, SIB, simple SIB, VIC, NOAA, CLM, JUICE, cable, etc. Each model, just like a final product, which consists individual pieces. And for each piece, there are different ways to do it. But how do you assemble the whole thing together really depends on the model developer's understanding, experience, and preference. If that's the best way, we can ask many science questions, such as, is there a synergy among different processes and parameterizations? Is there an optimal combination considering these processes and parameterizations? And do existing parameterizations possess typical signatures or exhibit typical patterns in simulating energy, water, and carbon balances? And we can also ask, is there a modular framework that would allow us to address uncertainty quantification, seasonal forecast, things like that. You can also use this framework to look at interactions between biogeophysics and biogeochemical processes. So how can we use what we have learned so far to guide model developed to represent the ones I just described? We have seen two schools of thought. The first school has been really familiar to meteorologists because many land models are developed by meteorologists. Another school is by model evaluators. This school represents scientists from training or background in system engineering. For model developers, we are familiar with these things. First of all, we are interested in increasing realism in representing key processes, understanding feedbacks, interactions, just like microphysics, cloud microphysics, everything similar to those fields. So we want to also maintain synergy between land model and other modules in the host atmospheric model. The ones you develop a land model, you want to use it for past, present, future climate, and also for observational weather prediction. Also, you want to generalize the model development from a limited area where you have observations to other areas you do not have observations. But for modelers, for model evaluators, this is what they consider. Have you addressed model uncertainties? Because a complex model has many parameters. Many of them cannot be measured, but they have to be there for convenience. But they will influence the model performance. So what is the best way to do this, to address the reconcile the difference between the two schools? This is my way of seeing things. I think we need to consider the model uncertainties coming from forcing, the validation fields, parameters, and of course different models available. And given a model, you can always add on different pieces like groundwater, dynamic vegetation, or nitrogen cycle, and dust cycle. You can add more components to it. So, but when we evaluate our model to further develop new processes, we really need to consider this overview. We need to have this overview. Because with this in mind, we'll have a better understanding of whether we are over-parameterized or under-parameterize the processes. As an effort to reconcile this, my former students have been publishing quite a number of papers in the past. Many of those papers have already received quite a bit of attention in the model evaluation community, such as a paper like this one, Improving Land Surface Model Hydrology is an explicit aquifer model better than a deeper soil profile. And a second paper by this student, Lindsay Garden, focusing on model performance, model robustness, and model fitness scores, a new method for identifying good land surface models. And also we talk about the parameter uncertainty, parameter interaction. So these results, these papers have been really useful for us to draw experience in our further modeling effort. As a request by NOAA, so I organized this workshop and jointly with Bob Dickinson, we invite scientists from many operational centers in the US, like NSAP mainly. And you can see it here, Bob Dickinson, Dennis Lettermeyer, Jim Shuttleworth, Paul DeMeyer, and Mac Egg, and Krista Peter Ledard, and Randy Coster from NASA, the usual suspects from the operational community. So with that, we launched NOAA MP, and it's evolved from original NOAA LSM with the key references published in JGR, and the original NOAA LSM was recoded based on standard, based on CLM standard, because we think CLM is a much better coded model. So recode NOAA MP to meet the high standard as you see in CLM. Also, we introduced the better land memory processes such as deeper snowpack and unconfined aquifer for groundwater, interactive vegetating canopy for transpiration and photosynthesis, and separating canopy temperature from ground temperature, allowing the photosynthesis to be introduced. These are two papers. Next, I'm going to show some quick examples of the results from NOAA-MP. This is a dynamic phenology model based on Bob Dickinson's 1998 paper. However, this work, even though it's very good in representing vegetation phenology, leaf area index changing with season, but did not get adopted in CLM. So we adopted in NOAA-MP. And turns out the model is doing a pretty good job in representing this model area and the modeled green transpiring vegetation fraction when you compare the modeled values with remotely estimate values. You look at the big and the broad patterns in tropics or in mid latitudes versus in high latitudes, model is doing a very good job. Also in comparing this is from a paper which is being reviewed by JGR. You can see the different regions in the US looking into the model area versus the observed area from the blue is the older version and the red is from the new version. You can see the new improved vegetation phenology is doing a good job in representing vegetation behavior across different seasons and across the US. We're also using other observations to evaluate a model, such as this Greece gravity recovery and climate experiments. They measure the total water storage change. They measure gravity change, but from that you can infer water storage change over large river basins. So we use those to evaluate the major river flows flowing to the Arctic Ocean by using Greece data set to guide this model development effort. By the way, CLM was also enhanced by the same logic using Greece to evaluate hydrological parameterizations over large river basins. Actually, CLM may be one of the only models participating in IPCC with Greece evaluation, validation of its large-scale water storage. For snowpack, we use the measurements from Rocky Mountains to compare different snow models. We all know that CLM has a good snow model, but NOAA-MP also has a very good, has simpler but a very good snow model as well. You can see that overall, among models, including VAKE and other models and the original NOAA, CLM and NOAA-MP overall giving the closest results compared to observations over the measured snowpack in the Rocky Mountains. So we think that the model meeting the earlier expectations we did design the model to have. And this multi-parameterization concept indeed representing multi-physics and multi-hypothesis testing. I'm going to talk about that in the next few minutes. So here is the core part, the central part of NOAA-MP. In addition to its enhanced realism in snowpack, in groundwater, in dynamic leaf phenology, the model also allowing different options to be introduced. For example, we just identified 10 different processes, hydrological, ecological, and biophysical processes. And you can add more if you want. This is just the point I'm going to make. For each process, you can take off-the-shelf schemes. And some have 2, some have 4 options. And then doing the math, they can one model, one framework, give you many, many combinations. So we have lots of young students. This is the work I like our students to do, perform all these experiments, running long experiments on global scale, at a regional scale, and seeing how we can get optimal combination, if there's optimal combination of schemes. Here we're not talking about parameters, talking about individual parameterizations. If we have an optimal combination of parameterizations for realistic simulation of water balance and energy balance. We have not done like thousands of experiments yet, but on global scale, what we have done is at 1 degree by 1 degree, 36 experiments. But interesting results can be found from the 36 experiments. You can see the model, because we are using observed meteorology, like precipitation to drive different 36 combinations. You can see precipitation is linear. And then precipitation is partitioned into runoff and ET. And the 36 experiments line up nicely. But they can be clustered, all of them, if you look at like ET, evapotranspiration, for top 1 meter soil moisture, 4 distinct clusters are showing. And within each cluster, you have different variants because of other variations in the options. But this, the 4 clusters are merely dictated by runoff options, clearly showing out of the 36 combinations, runoff is an option, is a critical option to determine water balance and the soil moisture and ET. That's for global large river basin evaluation. If you use the detailed, more dense data sets from, say, the Mississippi River, overall has lots of measurements. We run the model at a finer grade, much finer than 1 degree. This is a quarter degree, 1/8 degree. And then you can do the similar Taylor plots. Here you can see whether you use a dynamic vegetation with that option on or off. You can see how the 36 experiments are lining up. Basically, if you have option off, no dynamic vegetation, then the results are slightly worse than option on. If you introduce the Jarvis type of option to compute stormwater conductance versus a Bowberry, you get another distinct behavior. And if you use the different soil moisture limiting factors for transpiration based on SABE, CLM, and NOAA, and you get them all mixed together. So no distinct separation. But if you use runoff as an option, you can see 4 distinct clusters, the blue, green, and this light blue and red. So 4 distinct colors. This is consistent with what we found on the global large river basins. Those for offline studies. Next, we want to see in the coupled, when you couple those different options in WRF and see how seasonal, how the different combinations would improve water balance and temperature on a seasonal time scale. I'm not going to talk that too much in detail here. Here we also introduced additional 2-dimensional groundwater and river interaction. That is another option for groundwater dynamics. Here just a result, you see that with the more realistic 2-dimensional groundwater, you can see you have negative recharge. This means the deep aquifer will supply the water in the dry seasons to supply moisture needed for transpiration. So therefore, the soil moisture profile is very different from without that 2-dimensional groundwater river interaction. And as a result, latent heat flux different. The cumulative latent heat flux is very different from the other options. And for the looking at this table, NOAA-MP reduces the seasonal 2-meter temperature bias in WRF model, also the 2-meter dew point temperature bias. You can see NOAA-MP overall showing the reduced bias. Next, we introduce this NOAA-MP to NSEP's climate forecast system. Actually, the NOAA is considered as the next generation in this operational climate forecast system. And we just got a grant, even small amount, but is useful to support a student barely to do this further investigation to see if we have optimal combinations we can introduce that to the seasonal climate forecast. So here is a quick result. You can see that this is the default NOAA in the CFS. This is NOAA for this is the bias, the difference from observations. You can see the large bias here and reduced in this new run. Again, this is the earlier result, and the further tests are being conducted. But the central message is promising. I'm going to skip this. This is from my former student's work, showing when she introduced the default NOAA, then gradually enhancing its physical realism by introducing dynamic phenology and dynamic phenology of all vegetation and groundwater. You can see this coupling between the cloud base and this soil moisture in a nice transition towards what you could infer from now. These results are consistent with Randy Cost's results showing the central United States is a hot spot linking the soil moisture and precipitation on a seasonal timescale. So this is a quick summary of this work. And next, where do we need to go from here? First of all, you need to hear the wisdom from the pioneers, Bob Dickinson, Dennis Lentermeyer, and my former students visiting JPL, actually working in JPL with George Fisher, Dave Lawrence, Bob Dickinson, Dave Lawrence. This is a workshop in Germany, and Sarush, Eric Wood, and Mahanti from A&M, soil physicist, and Mike Eck from NSAP. He's too excited to go forward from the enchanted rock in central Texas near Austin. But we have to think, we have to make a careful step to move forward. And we just had this recent workshop 2 months ago. When you have models, when you have data sets, data assimilation is a must. Because all the models are wrong, even though they are useful, all the data sets could have bias as well. We really need to integrate their strengths. So I was proposing to have this multi-everything. So you have, we talk about couplers a lot. So you have subsurface models, land surface models, lots of subsurface models, like a 2-dimensional, 3-dimensional flow, really sophisticated, and surface models allowing above ground exchange with atmosphere. And also river transport models dealing with the human modification of rivers, reservoirs, lakes, etc. And with this linked framework, that would really conducive for lots of investigations that could be done in a much better organized way. Right now, no one has done this yet, but at the university community, it's difficult to get money to do this. But if here, Taiwan, you want to do this, I'm happy to collaborate with you along these lines. In the next few minutes, I'm going to do quickly, just showing a very quick write-down where we need to go from here. This is my group. The Logan in my group is one group, 2 models, work on CRM and NOAA and many other applications. And then develop this center, trying to promote more collaborations across campus. So this is a center trying to, because this center is based in geology, so we are going to work a lot with geologists, geomorphologists. We really like to have international collaboration, to deal with lots of challenges. In supercomputing, we've seen this Earth simulator. This is Stampede in Texas. It's faster than Yellowstone in Anchor and Wyoming supercomputer. And new challenges in land surface transformation, and new challenges dealing with extreme events, and challenges to help to inform society. And also trying to not just working on traditional land-atmosphere interaction, but including the biogenic emissions, and dynamic phenology and related biogenic emissions. So you can deal with direct climatic influence on BVOC and indirect climatic influence on BVOC through the leaf phenology change. Also, SOE, we heard a lot about SOE. That's not my field, but one of my former students took a challenge to work on this by collaborating with scientists from Chinese Academy of Sciences, from John Seifeldt group, and also from Wiedemeyer in NCAR. So you can really address the lots of linkage between hydrosphere, biosphere, through the biogenic pathways. You can also use that to address regional climate change. And dust emission, I mentioned this to Phil. This is ongoing work for my student. We develop a new usability map and also a new land surface type for Middle East and for Africa to deal with dust emission. We're also trying to address the linkage between watershed and coastal waters, and by have a better handle on continental water dynamics to address those questions that used to be asked by former President George Bush. Very simple questions, but none of those questions are easily addressed, easily answerable. When you really deal with water quality, water quantity, you have to have data sets. You have to deal with these kind of inventories for each county, each nation, and each continent. And we have remote sensing observations, how to use that, how to use surface observation, how to use them, and data assimilation is a key. So this is the ongoing work by my group to use DART in NCAR, and linking DART and CLM, we developed this new extensible and flexible land data receiving system, trying to assimilate all things you could measure from space to develop mutually consistent data sets of temperature, soil moisture, runoff, ET, etc. So this is the ongoing work already published by simulating models and GRIS, total water storage change, and modest snow cover fraction. With that, I should stop here. I just have 3 minutes for questions. Sorry, it's not long enough. Thank you for your attention.
Thanks for showing a lot of work here. So. So, Phil first.
So I'm interested in in examining the sensitivity of the perturbations or the changes in the model when you change component the oscillation. How that compares with doing parameter variations. Also, I mean, it seems to be model A with variations in the parameters inside that model might produce a simulation which looks much like Model B does out of the box. So how do you isolate which is more important, the settings of the parameters or the change in the parameterization?
So far in our study, first of all, that's a very good question. We have been thinking about that, but we haven't got the satisfactory answer yet. But so far in our investigation, we only focused on parameterizations, and for each parameterization using default parameters. But next, we want to explore the uncertainty quantification using both parameterizations and optimal parameters associated with each parameterization. So I have a project funded by Chinese National Science Foundation but I cannot use the money in the US. So I can only hire postdoc and student within China. He's doing that right now. Maybe in 1 year from now, if I come back to here, I will give an update on that result. Yeah, one. Mm-hmm.
Have you tested the atmosphere and the land surface coupling strengths on different regions? For example, soil moisture is one of the key components.
Yeah, the coupling strength, that's related to Phil's question.
Yeah.
That's another one of the research questions we are going to address in the project funded by Chinese National Science Foundation to revisit Randy Costa's hotspot of coupling strengths. in the monsoonal region and non-monsoonal region. So we are doing that right now.
So would you be able to get the soil moisture data over East Asia, since you're funded by the CAS?
The CMA, China Meteorology Administration, they have more than 700 sites of soil moisture. But we are negotiating how to access that soil moisture measurements. Yeah. Currently, I have no answer, but we are working on that. We also want to know the quality of the measurements. We know they have more than 700 sites, which is incredible. But whether the quality is good or how detailed the measurements are, we'll investigate. Okay.
So last question.
He was mentioning soil moisture,
Yeah.
which is a very important parameter, but I also think each different parameterization scheme has their own interpretation of what soil moisture is. So each model, once they evolve, they would carry their own soil moisture signature. So when you do the multi-model, do you run the different parameterization on its own, or do you every time step average their results and move on?
Yeah, for that, actually, we are testing using NLDAS testbed, North American Land Data Simulation System. They have a testbed for the whole corners, continental U.S. at 1/8 degree. Actually, Ruby and her group collaborating with us. We are comparing original NOAA, a new NOAA MP, CLM, and VIC, the Dennis Letterman VIC model. We found NOAA MP for soil moisture variability, given limited measurements we have in the U.S., NOAA MP gives very good simulations. Actually, VIC and either VIC or CLM, the magnitude of soil moisture variations are too low compared to observations. NOAA MP does the best job. But that's what we have found so far. We want to do more evaluation by perturbing parameters, also by perturbing by changing different combinations. Again, that's very computationally intensive, but again, like more, our code is downloadable from the NCAR website. A young student here, if you're interested, you're welcome to test them yourself.
Okay. Thank you. Let's thank Liang Yan again.